Stan, thank you so much for joining us today. I know you and your team are very busy, and I do appreciate you taking time out to share with the community on this topic. So thanks again.
Yeah, no problem. And thanks to everybody. Thanks, Mackenzie. Thanks, Tim, for taking the time to listen in on this webinar. We know how busy everybody is with managing their water systems these days. So hopefully this is going to be beneficial to those of you that have taken the time to join the call. So the topic today, I'll get right into it. Stop the silent rain, right? Really what we want to talk about is what is the, I guess, bottom line when it comes to investing in continuous monitoring. And to do that, I'm going to talk a little bit about some of the background in non-revenue water. A lot of this, I apologize, is going to be information you guys already know. But if there's anybody on the call that doesn't have some of these definitions down, it's all here for reference. So I won't spend too much time on this. We all know by now, non-revenue water is a huge issue in North America, right? About 1 in 5 gallons that we produce doesn't make it to the consumer, right? So that's 20% of the water that we are currently supplying is not getting to the end goal. And to put that into perspective, you can see on the right-hand side, right? This is the US, $6.4 billion in non-revenue water in 2025. For main breaks, it was $3 billion, right? And these are the GDPs of some countries, right? This is how much was spent on wildfires in 2024. So, it's a huge issue. And there is a lot to also, recoup, right? There, $6.7 billion, $6.4, $3 billion. So there's a lot more we could do to produce this number. So what is non-revenue water, right? Many of us are going to be familiar with AWWA and M36. This is kind of one of the standards that a lot of us look for when it comes to defining non-revenue water, water audits and water balances and whatnot. So this is the water balance according to M36, right? And we can see inside this water balance, when we talk about water loss, we really are looking at this portion here. So non-revenue water, according to M36, is made up of unbilled authorized consumption, apparent losses, and real losses, right? So with that, the water loss is just the apparent loss and the real loss. And what's important to note here, when we talk about apparent losses, we're talking about water that more or less appears to be lost, right? Due to inaccuracies, your meters of your sensors have drifted over time, or water that has been taken out of the system without authorization. Real losses are leaks, right? Water that's lost to any kind of leakage, and there's different kinds of leaks. But the more important thing to note here is that in the US, real loss accounts for 87% of all water loss, right? So there's a significant opportunity there to tackle real loss specifically. And that's really what we're after with continuous monitoring. So what types of real loss are there, right? So we talked about it's all leakage. And M36 goes on to define that real loss is one of 3 types. You've got reported leaks, which are breaks, right? They get called in. You get unreported leaks. So these are going to be, the non-surfacing leaks that I think a lot of utilities are struggling with right now. They don't surface, so it's hard to detect them without a dedicated means like acoustic surveys, loggers, continuous monitoring. And then you have things like background leakage, excuse me, which is basically defined as leaks that are too small to be detectable using these acoustic means and whatnot, right? So the definitions of these they're not absolute. And over time, as technology gets better, you're going to see more things that would have been classified as background leakage become unreported leaks because we're going to have technology that can, detect these leaks earlier and earlier. And that's really the point of continuous monitoring, right? So just kind of this is a generalization or big overgeneralization of, what helps with what. But it helps to think of it this way. So when you talk about reported leaks, breaks, and things like that, it generally something like a preventative approach, pressure management, making sure that your system doesn't cause any overloads at any point, that you're managing that demand will have some good results in terms of reducing breakage. When it comes to unreported leaks, you have to find them, right? You have to find them some way. So that's going to be using a detection approach. The most common in North America is still doing a leak survey. And then when it comes to background leakage, really, according to the definition, these are leaks that are very hard to find deliberately, right? So having kind of a systematic approach to it, a plan to do your pipeline renewals, inspections, things like that. Preventative approaches also help with this. That's why I said this is kind of an overgeneralization, but you kind of get the idea. There's really three separate schools of thought when it comes to how do I deal with these things. Which means, as a utility, most utilities deal with all three types, right? So you're going to need some strategy that incorporates elements of all three. And that's really where we'll talk about continuous monitoring. But when it comes to any kind of leak, right? Also from M36, we break that leak into the runtime of that leak into three stages. So the awareness stage, the A, the L stage, the location, how long does it take for you to pinpoint the leak? And then the R stage, right? How long does it actually take for you to repair the leak? So when I go back to the three types of leaks, you're just using an example, right? This is just for illustration. When you have a reported leak, the entire ALR stage is very, very short, right? You've got a leak that appears, someone calls it in, you know exactly where it is. You have to go and repair it because the flow rate is going to be very high, typically for those leaks. Unreported leaks, you're going to have a longer awareness stage, right? You're really not going to know about it until you go out and actually do that survey, right? Or maybe it becomes a surfacing leak or a reported leak. And then location can also be tricky at times, because these leaks are inherently subsurface and difficult to to hear, depending on the system. And then background leakage, right? So this is one where these leaks run for um, very, very prolonged periods of time. And I'll show an example later where we think we see a background leak that turns into an unreported leak that turns into a reported leak. So sometimes these three types of leaks are interrelated. One becomes the next and so on and so forth, right? But the idea is this awareness time is something we want to keep in mind. And when we think about how much water is lost to each type of leak, it's really, this is the flow rate on the y-axis time. So the total amount of water lost is really just the area right under this curve. So looking at the size of the shapes, you can see usually for these reported leaks, these breaks, although they have very high flow rates, comparing it to the runtime of unreported leaks and background leakage, you lose a lot more water on average to these two types of leaks, especially unreported leaks. Right. So this is kind of the main takeaway here is that, that water loss, a significant portion of it is going to occur during this awareness phase. And so this is where continuous monitoring comes in, right? The way that I look at continuous monitoring is it really is trying to mostly tackle this unreported leak problem, right? That's at least what we see in industry right now. A lot of these technologies are centered around leak detection. Some are centered around pressure monitoring, right? But the idea is a continuous monitoring strategy is going to give you a little bit of leverage into all three of these categories. So taking our hydrant.AI solution, for example, what do we do? Right. So for acoustic leak detection, it's perennial for us. We have the acoustic sensors, the hydrophones in the device. We're listening for leaks every day. You compare that to a leak survey where you only get a snapshot every time you send that surveyor out, right? So it could be once a year, once every 4 years if you're rotating around your water system. So that's one of the benefits, right? Is having that perennial acoustic leak detection reduces that awareness stage. You know about that leak sooner, you can cut down on the water lost during that time. We do specifically hydrant.AI, we do a lot with pressure anomaly detection. So we take that pressure data from the sensors. Each utility is different, each water system is different, and it learns the patterns and is able to kind of identify when you have significant patterns or deviations from your normal pressure patterns. Hopefully that's you kind of become aware of that before it becomes a larger problem down the road or a break. For in terms of how we can encroach on hearing background leakage, we use a hydrophone. So the difference between a typical kind of logger is it's mounted onto the surface of a pipe, or a fire hydrant outside or a valve, and that's not going to be as good as a hydrophone where you're directly in the water column, right? So when a leak happens, you can hear that sound travels much more consistently through the water than through the pipe, especially for PVC. So that combined with our use of signal processing, machine learning, lets us hear more leaks that, again, typically may be classified as background leakage before. Um, but that's kind of where a continuous monitoring approach can try to check off all the boxes. Again, you still need a holistic approach with these other strategies in mind. It's just this is what continuous monitoring brings to the table. It kind of dips into both of those as well. The last thing there is, we also provide that real-time pressure and temperature data. So it's just another sensor in the system, right? So whereas one way to monitor for background leakage is having flow meters installed throughout the system and monitoring for deviations there. But this is just a little bit of that extra add-on for us. Okay, so continuous monitoring, that's great on paper. How do we actually estimate the ROI of continuous monitoring? Right, so there's a couple factors, a couple big factors that come into play. So, one of the things is geographic factors, right? So where are you located? How expensive is water? How available is it? What's your method of water treatment? It's going to affect how much it costs to you to supply, as well as to the customer, right? So we can see average monthly water bill by state. Sorry, in 2025, you can see the Pacific Northwest region, the highest by far overall. You can see kind of around the Great Lakes where we're located here, probably the lowest, as well as this kind of West Mountain region, some of the lowest. You can see the disparity, right? It's 100% difference in the average monthly water bill. And that's going to really affect how you make a decision in terms of how you implement and what you implement with continuous monitoring. Another factor that's important is population density, right? So, how many metered connections do you have per mile of pipe, right? When you think about putting a continuous monitoring system, a permanent monitoring system in, right, it's got eyes on a certain length of pipe radiating outward from where you install that device. And the more connections you have within that within that radius, the more bang for buck you get. So this is just kind of showing an example of downtown Toronto. You can just see this is not the distribution network, but you can infer, right, how many connections and how much pipe you have. These are on the same scale, right? This is another town in Ontario, Emo, and you can see just the difference, right? So if you're a water system out here, your kind of approach to evaluating continuous monitoring, your strategy to deploying it is going to be very different depending on or compared to someone like Toronto. Okay, another one is pipe material and age, right? So average break rate is going to vary significantly depending on the type of pipe material. Older pipe we know is more likely to fail, but you can see this is taken from a report by Utah Water Research Facility in 2023, and you can see a cast iron, 3 times the failure rate of AC, PVC, very low failure rate. So the type of pipe material you have is going to significantly impact your potential ROI as well. So what does that really mean? Well, it translates to a lot of complexity when it comes to figuring out what you're actually going to get back when you invest in a continuous monitoring system. So with that in mind, internally at DWS, we wanted to develop an ROI calculator for utilities that, maybe your utility that's looking into continuous monitoring and you want to understand what am I going to get back potentially from the system, or you're a utility that already has hydrant.AI and you want to be able to quantify the ROI of leaks that you find in the system. So some of the goals we had, right? We want this calculator to take into account the parameters that are specific to each utility. So what is your percent non-revenue water, the size of your network, total length of your water mains, annual volume of water supplied, those geographic factors, population density, pipe material, right? And this is important. Wherever possible, use data from publicly available sources. So things like average break rate, water costs. Anytime that we can use publicly available data and we can cite that data in the calculator, it helps build confidence and transparency in the calculator. And kind of to add on to that, there's going to be some things, obviously, this is an ROI calculator for our specific continuous monitoring solution. So there's going to be, parameters in there that will not be publicly available. And the important thing for us is to calibrate these parameters using real world performances, or you'll see in the case studies, are the numbers that we're generating from that calculator in line with what we've actually seen from these deployments. So this calculator is going to be available on our site for anybody to use, hopefully in the next month or two. But I won't make that promise on behalf of the developers. And there's also going to be a white paper that goes into all this information in more detail. So this is, don't worry too much about taking in everything here. Just to show some examples, this is that a plot that's generated. This is the cumulative water savings. And this particular iteration of it, this plot is looking at differences between geography, right? So you can see, I've just picked a fictitious utility, DWS Waterworks. It's got some average unit water cost to the consumer. And you can see how that compares. This is the national average across the US, right? If you're somewhere in the Pacific Northwest, you're in this upper bound of savings. And then if you're in the West Mountain region, you're in this range. And this is generated this is a device spacing we have for our units. I'll get into that in a few slides. So this is really just to show, again, there's sometimes a large disparity, right, depending on where you're located and the type of ROI you can get from continuous monitoring. Another version of this calculator, so you can also look at, again, population density, right? So similar to that last plot, you can see if you're high population density, you're going to be on the upper end of this curve, right? You're going to have a higher expected return on your investment as opposed to low population density, and you're going to see less with everything else kind of held constant. And then this is the spacing piece, right? So one of the things is when you have a continuous monitoring system, you're going to have, let's say, 10 units, 5 units. How far apart do you space them? So one of the things we looked at was, what is the optimal spacing? And again, that is very closely connected to this ROI piece. So we wanted to evaluate with those deployments that we have in the field, where do we see the most success, right? So in this case, the bounds, so we have two cases, 1,000-foot spacing is the blue, 1,500-foot spacing, so that's putting a unit on every 3 hydrants versus 2 hydrants. The bounds here are the population density, right? So you can see, there's a lot of cases where the closer you put the units together, the more leaks you're going to find, right? Because there's going to be a lot of small leaks and background leaks that require a closer spacing to be able to pin down. However, you can see if you are a higher density utility, right? You're downtown, you're mostly a lot of clustered connections, you would benefit from a larger spacing, right? Because there are other benefits that are not captured in this particular comparison. For example, when you put the units farther apart, you are getting more visibility on pressure in a larger portion of your system, right? Spacing the units close together is good for leak detection, but you're going to lose out on pressure monitoring. So there's some benefits that are not kind of incorporated into this calculation here. This is just an example. And again, we'll have a paper that explains this in more detail. I want to jump into some of the case studies. So, how do we actually show that continuous monitoring works in terms of ROI? So one that we did recently was with King County, right? There's a pre-existing leak, meaning there's a leak that's been in the system. We don't know for how long. We install our units and we're able to detect that leak right away. That's one of the things that we can do with our hydrant.AI platform. And then we can repair that leak. So that's the leak there being repaired. This is for King County, WD-90 in Washington, US. So they've got 7,000 service connections, 110 miles of water main, mixed material. This particular area where we deployed was AC. and fairly large leak, right? 29 gallons per minute, high pressures um, in this particular zone. And this is a pre-existing unreported leak. Now, the actual time to detect, locate, and repair, once the units were installed is roughly less than 2 weeks, right? But if I look at that in terms of the implications for the next leak of this nature, because again, it's a pre-existing leak, meaning we don't know how long that leak was running prior to the start of monitoring, right? So it could have been going for months, it could be just a few days. But the idea is, you know, with the continuous monitoring in place, the next leak that you see of this nature, you're going to be able to follow this timeline. And you're going to be able to detect, locate, and repair that in 2 weeks, as opposed to having it run for, and months or years. So we found in this case, that leak would have cost the utility $6,700 a month in lost water revenue. So if you let that leak run for 1 year, just one leak, that's $80,000, right? When you have continuous monitoring in place, that leak is only going to cost you $3,000, right? You're going to find and repair that very quickly. So the idea here is to be able to demonstrate with any solution, any technology that you implement, and what's important to us, obviously, is to demonstrate that you can get your ROI back in some tangible way, in some reasonable period of time. And with us, we're trying to show the value of continuous monitoring. Yes, it's a permanent long-term solution, but the ROI actually comes very quickly, right? You're going to get a lot of that value back in the first year, and then you're going to continue to see value because what we see with a lot of these areas where you have high water losses, you fix one leak, another one is going to happen, right? It's not that you fix all the leaks there and then that's great. You can move the unit somewhere else. You're always going to get leakage. It's always going to be this kind of continuous cycle, this battle with aging pipe and whatnot. So you're going to see that value return year over year, most likely. So another example here is in close to us, region of Waterloo, and specifically the township of Ayr. Very small, very, very small, excuse me, distribution network. You can see just 15 miles of pipe, services, sorry, and 20 miles of water main. Mixed material, but mostly PVC. This is a very small leak that we found here. And this is a few years ago that this particular case study was kind of put together. This is really during the phase where we're trying to still understand what can we do with hydrant.AI, right? So how early can we detect a leak? How well can we track these leaks? And what does that translate to? So for this particular leak, we did an interesting study here, right? This is the leak energy. So this is one of the things we track with our machine learning models. You can kind of think of leak energy as it's correlated with leak size. Not one to one, but you can think of it that way. And you can see this is a hydrant that was very close to this leak. So you can see in October, there's a certain baseline, right? And then it starts to slowly creep that leak energy. And we can think of that as background leakage, right? And then you can see how long it stays as a background leak, and then boom, something happens in the system. It turns that background leak into an unreported leak. The flow rate is going to go up, right? And then finally, in the span of a few days, it's going to go from that unreported leak to a reported leak. It ended up being a break here. So the idea here is that like this small leak, again, water is much cheaper here. It's still $43,000 a year in lost revenue, right? But the other kind of takeaway here is that, this shows background leaks and how they can turn into unreported leaks and how they can turn into reported leaks. So the benefits of being able to detect these leaks early is not just the water savings, but also you're saving, the time and resources, right? You're saving the emergency repair costs. And you're going to prevent, a lot more wear and tear on your system. You're going to prevent some of these leaks from developing to the next stage. So that's pretty much the kind of crash course that we have here on ROI. As I said, the ROI calculator is going to be up on our site shortly so that you can play around with that and you can punch in the specific information to your utility and get an estimate that is going to be unique to your circumstances. A couple things here. Again, thank you again to WWA. Thank you everybody for taking the time to join the webinar. If you want to learn more about hydrant.AI, the link is there. Any of the case studies that we showed here and more, there's a link there to download those. If you want to get in touch with us directly, there's the contact information and the references if you want to read more about kind of where we got these facts and numbers from.